properties of functions. All right. The first thing we want to talk about is the odd, even, neither test for functions. We can determine if a function is odd, if that function is even, or there are quite a lot of functions that are neither of those. So the way that you would do that, there's one test that decides it all, and that test is to find f of negative x. What does that mean do? Plug in negative x into the function. And simplify. That's all. That's what we're going to do. And based on the result, we're going to be able to decide if the function's odd, even, or neither. If a function, if f of negative x is back to the original, that's exactly the same. That's what that statement says, is that when I plug in a negative x, I get the original problem back. That's what that notation says. If I get the original problem back, f of x is even. If I plug in negative x into the original function and I get the opposite back, that means everybody's sign changed. Has to be everybody. It's all or none. Okay? So everybody's sign changed, then f of x is odd. We're going to get some examples of this in just a minute. Some actual functions. If I plug that in, and it doesn't give me the original back, or let's just do, or, because it's not a negative statement here. If I plug in negative x and I don't get the opposite back, I get anything other than that, kind of a mix of that. So some of them signs changed, but some of them didn't, that sort of thing. So if I get something that isn't one of these two, guess what it is? Neither or neither, depending on where you're from. Okay, neither odd nor even. Okay, so if we don't get the exact original back, then or the opposite, which means everybody's sign changed, then it's neither. Okay, so if it's a mix of that, okay, even, you get the original back. Odd, you get everybody's opposite signs. Okay, all right. Take your earbud out of your ear, folks. I'll say it one time, and I won't say it again. If you got earbuds in your ears, don't wear them in my room while I'm teaching. That is disrespectful. I know it's a cool thing to do right now, but it's disrespectful. So don't do it. All right, let's do some examples. Determine if the function is odd, even, or neither. Example A. Here's our function, f of x is equal to negative 3x to the fourth plus 6x squared. All right, so if we're going to test that, what's the real test that we should do in order to determine if that is odd, even, or neither? Plug negative x in. That is the test that we need to prove that something is an even, an odd, or neither of those. So plug in negative x to the fourth power plus 6 negative x squared. Okay, so when you simplify that, order of operations says you got to do the exponent part first. So when you take a negative something and raise it to a fourth power, what does it turn back into? Positive something. So positive x to the fourth times negative 3 is still going to be negative 3x to the fourth, right? Same thing here. When I take negative x and square it, that's going to be positive x squared, right? And so we have positive 6 times positive x squared, which is back to positive 6x squared. Is that the exact same thing as the original? Yeah, so what do we know about this function? It's even. And this is the proof that that's happening, okay? So there are shortcuts. We'll discuss those as you talk about them, okay? You'll see as we do several of these, you're like, oh, this is always the case. But this is the proof that's the mathematical proof that is an even function. Algebraic proof of it. So we had f of x is 3x cubed minus 5x squared plus 6x. And we want to, again, determine if that's odd, even, or neither. So the test for that is to do what? Plug in negative x and work it out. So 3 negative x to the third, 5 negative x squared plus 6 times negative x. Okay, so if I take a negative x and bring it to the third power, what's it come back out as? Negative x cubed. So that's going to be changing that to negative 3x cubed, right? And then the second piece, we got negative x squared. That's positive x squared times negative 5 is negative 5x squared, right? And then here, 6 times negative x would be negative 6x. Is that the exact same as the original? No. Is it the opposite of the original? No. This guy in the middle had the same sign. So this one would be a neither situation because it did not match the original or have the opposite signs of everything in the original. It's real easy to recognize there. Not a tough test. It's easy. Very, very simple to do. Let's get another function here. G of x, negative 8x to the third minus 5x. Again, the test for odd, even, or neither. Plug in a negative x. So negative x to the third, we've done that already. That's negative x cubed. Negative x cubed times negative 8 would be positive 8x cubed. And negative 5 times negative x would be positive 5x, which is the what to the original? It's opposite. Everybody's sign changed. It has to be everybody. It can't be just one piece. Got to be all of it. So this would be an odd function. What's the shortcut when it's a function with an equation like that? Exponents. Yeah, the exponents. Example A, what was every exponent? It was an even exponent. Example C, every exponent was an odd exponent. What was the difference in example B? You had even and odd both in there. So that's the shortcut to it. This is the algebraic proof of that. So if somebody says prove that this is an odd, even, or neither function, you got to show that that's what's happening, but you should know the answer just by looking at the exponents. How that can help you out there. Okay. We'll build upon that idea of odd, even, and neither as we kind of ramp up in different functions about that. So graphically is not quite as easy to do. Algebraically, it's very easy. Graphically, some people are really good at it because it's kind of like the symmetry idea that if you've got to be able to see it folding in your head a little bit. Some people have a good spatial sense and they can kind of see that. Most of your creative folks can do that are do the art and stuff like that. But graphically, we'll do a few examples of that for odd, even, and neither. Okay. It is directly related to that symmetry that we kind of introduced in section 2 there. Symmetry with respect to the y-axis. That's going to be an even function. You can fold it. I think the wording we used in section 2 was across instead of with respect to. It's the same thing. So if it's symmetry with the y-axis, that means you can fold it this way across the y-axis, and it matches up, and that would be even. We'll look at some pictures in just a minute of that. And then symmetry with respect to the origin is odd. Capitalize it. And again, to be symmetric about the origin, you got to be able to fold it this way and then again this way, and it match up. Doesn't necessarily mean that it has to have y-axis symmetry and it has to have x-axis symmetry, but you've got to be able to visualize folding it across the y-axis and then folding it down across the x-axis, and that can be that. Or if you can visualize a y equals x line going through there and then folding it diagonally. Most people, the vertical and horizontal fold is a little easier to visualize than a diagonal fold, but it's a diagonal fold if you do it that way. All right, so even, it's got to be symmetric about the y-axis. If it's odd, it's got to be symmetric about the origin. Anything else that's happening, it's neither. Okay, any other situation is neither. So I'm going to try to sketch a few pictures here of some graphs and make some of that happen. So coordinate plane, just sketching a graph here. We don't even have to have tick marks on this thing. We just want to draw something that is pretty close to. That's pretty good. What would that one be? Even. Symmetric about the y-axis. If I fold it across this line, we can see that it should match up there. That's what I'm going for. So, an even function. It didn't work out too good. That was a little tougher to draw. But can we see that if we fold it across the x-axis and then down across the y-axis, that they would match up there? This is with respect to the origin. All right, so this is odd. It's not very often in any sort of math class you're going to be asked to determine odd and even with graphics and no equation given. But it is handy to be able to glance at one and get a good idea whether it's odd or even, or if it's even. Even functions have a lot of things that are neat about them. Odd functions don't have quite as much going on for them that's special. The functions that are like that would be obviously what? Neither. You can tell. It's easy to look graphically and see even. Odd is a little tougher. Neither is pretty easy to see out of that. But even is the easiest one to see symmetry or neither. They're both pretty easy to see that they don't match up, that idea. So being able to look at one and just kind of get a quick idea of whether it's odd, even, or neither. I'm not going to give you one that's questionable usually on it, and the book's really not either. They're not gonna put one that's borderline there, because it's, unless you've got a little bit more to go on, it's very difficult to tell. All right, so the next thing we're gonna do is kind of one of those things where we're looking at intervals over a graph. So this kind of harkens back to what we were doing with the first part of section 2, where we're looking at a graph. So we're going to find the increasing, decreasing, and constant intervals for this particular graph that I'm going to draw. So I'm just sketch what I'm drawing here. It doesn't have to be perfect. I'm going to put some ordered pairs in strategic locations so that we can discuss a few things. So I'm going to -6. That ordered pair, that dot right there is -6, 0. It is a filled in dot. -4, -2. That's better. Yeah, let's make it -4, -3. That's what it looks kind of like. And then the dot up here at 0, 2. And another one here, 3, 2. And then +6, -2. So I'm going to draw the weird looking graph that goes with this. Okay. Yeah, that's what's going on. All right, so let's first talk about the domain of that graph. Can I kind of just build upon what we already know? What's the domain of that graph? -6 to +6, parentheses or brackets? Why brackets? That's correct. Because the dots are what? They're filled in, right? So if they were empty circles, then we'd use a parenthesis, but because they're filled in dots, the domain here is going to be from -6 all the way to +6 with brackets on that because we're including those. Let's talk about range. That was something we discussed. So range are the y values. What's your lowest y value? -3. And your highest y value? 2. Brackets or parentheses? Why brackets? Dots are filled in, so you got to include them. Okay. All right, so there's the domain and range. So now let's get into the increasing, decreasing, and constant. So we kind of talked about this the other day. If something is increasing, which direction is it going? Up and to the right, correct? If it's decreasing, it's going down and to the right. If it's constant, it's straight, flat. All right, so let's just start on the left and work our way across that graph. So we're starting at -6. That's the lowest value on our domain, so we're starting there. It's decreasing from -6 until it gets to where? -4. And it stops decreasing at -4. So we've got a decreasing interval there. I'm going to go from -6 to -4. Notice I use parentheses on those because I'm not sure what it doesn't do anything, to the left of -6. I don't know what's going on there. There's no part of the graph there, so we don't know what's happening. So at -6, that's just where it starts. So I'm going to use a parenthesis there. And then this is the turnaround spot, so it's really not doing any, it's flattening out right there. From -4, what's it do now? Increasing until I get where? To 0. The increasing interval from -4 to 0 And what's it doing at 0? It's constant until I get to where? 3. 0 to 3. And then what's it do next? Decrease from 3 to 6. So we happen to have 2 decreasing intervals out of that. Okay. It really is that simple. Don't overthink the increasing, decreasing, and constant intervals. It is that easy. Okay. Don't overthink those. The lid stayed closed.
Yeah.
When? It's going to be a good Monday. All right. Let's talk about maximums and minimum. Maximum and minimums, there are local maxes, and then there are absolute maxes and mins. Okay? Local max and absolutes. Locals, we've got to know, what does local mean? Close by, within a small area. Okay, so if I say something local to Adamsville, Tennessee, we're talking probably within an hour of driving. Right? That's local. That seems about right nowadays. An absolute would be what?
Farther out.
Further out. How far out? As far as you can go, right? All right, so if we're talking about functions, if we're talking about an absolute on a function, what's as far as you can go? Depending on the function, right? On a function, what governs how far you can go? The domain, right? Your domain tells you how far you can go. If we're looking at a local max, we're going to talk about a small interval, a small snapshot of our whole function. A absolute, we're talking about over the entire domain. Okay, so local is over a smaller interval. Absolute is across the entire domain. Okay, an absolute max or min is, when we're talking about maximum and minimums, we're talking about the y values. Over these intervals, we're talking about x value intervals. So they're going to tell you, okay, what's the local max between -6 and +6 if you look at the graph above us, right? In the last example. We got a domain. That a local max, we take a snapshot of that. So what's a local max between -4 and 2, something like that. Where if they said, what's the absolute max, you're looking across the entire domain from -6 to +6. And that's the difference in those two things. All right. Get your textbook out. We'll use a picture there instead of having to draw one and all that. So looking at page 234 in your textbook. If you don't have yours, just look on the slide close to you. Page 234. Use one of the pictures there. All right, 234, figure A there at the top. Figure 26, and then let's look at A part. All right. Page 234, figure 26, part A. All right, this is going to be example H. Number 1, find a local max over 2, 4. This 2, 4 is a what? It's an interval. That interval includes 2 and 4 are what kind of values? What are they, x or y values?
Y.
X values. Local intervals that when they tell you to look at an interval, they're going to give you an x interval. Okay, location on a graph is x intervals. Okay, x intervals always. Okay, when we were reporting where things, if they said where is f of x greater than 0, we were telling what x values that was. Okay, so here they're looking for a local max over a certain interval. This is an x interval. It's an interval of x value. So from 2 to 4, we want to find the local maximum there. So if we look at that graph between 2 and 4, what is the local max? No. What's the ordered pair? 3, 6. This is an ordered pair. It's a point. Okay. A local max, or up here, max and minimums are y values. Okay. The highest y value on that interval. We're looking at all the x values from 2 to 4, and we're finding the highest y value that goes with any of those x values. So we look at that graph. We've got a peak there at 3, 6. That's the ordered pair. Okay, 6 is the y value that goes with that. That local maximum is at the point 3, 6. And when we're looking for maxes and mins, we're looking for y values that are the highest or the lowest over local. It's over a certain interval. Absolute, it's across the entire graph. Okay. Same picture. Let's just do another question off that same picture. Let's find a local minimum over the interval from 3 to 5. So looking at that picture, local minimum from 3 to 5, those are the x values I'm looking at. I'm looking at starting at 3. I'm going over here to 5. I want to find the lowest point in there because it's a minimum. Where's that at? 4, 4. So it's at the point 4, 4. And it's because not the x value is the lowest, but the y value is the lowest. It's location out of that. All right, where's the absolute max? And the absolute max, absolute min on that picture. Still figure 26, part A. Just looking at the A. The absolute max is at 3, 6.
Varsity cheerleaders are selling shirts, hoodies, and sweatpants. See a cheerleader or Miss Mainers.
Where is the absolute minimum?
There will be a basketball workshop
0,
from 2 until 4
1.
in the library.
The lowest y value on that graph is 1. And so 0, 1 is where that's at. So absolute local maxes and mins.
And
all right.
If you want to play tennis this year, make sure you see Coach Harbaugh. I need Carter Reeves, Shelby Fisk, and Wyatt Beach.